In today's video, we'll talk about SSRF, or Server Side Request Forgery. So, what is an SSRF? An SSRF, or Server Side Request Forgery, is a vulnerability that occurs when web application fetches a remote resource without validation on the user-supplied URL. It allows malicious users to cause a web server to send additional or manipulated HTTP requests to the resources of the attacker's choice, even when protected by a firewall. For example, here an attacker tried to send a direct request to the victim server, however it is blocked by the firewall. So what does the attacker has to do is sending it through the web server making the request on behalf of the user, because the web server has a trust relationship with the victim server. Then the victim server responds to the web server, which will then send the answer to the attacker. Now, what is the impact of it? A successful attack can result in any of the following: either access to unauthorized areas, access to sensitive data, port scan of internal resources, compromise internal services, reveal authentication tokens, credentials. So there are two types of server-side request forgery. We have the regular one where the data is returned to the attacker's screen, and there's also the blind one where the SSRF occurs, however, no information is returned to the attacker's screen. So let's see this example. We'll go over it together. So the instruction says, we are going to take you through some sample SSRF attacks and explain how they work at the end of the examples. You'll have to figure out one for yourself. Okay. So the below example shows how the attacker can have complete control over the page requested by the web server. The expected request is what the website server is expecting to receive, while with the section in red being the URL that the website will fetch for the information. The attacker can modify the area in red to an URL of their choice. So this is the expected URL, but this is also the part where that can be modified by the hacker. So the hacker, instead of sending this expected request, he modifies it to try and get the user. So as you can see here at the end of the expected request would be API/stock/item ? ID equal 123. So instead of putting /stock/item and so on, they modify it by user and try to see if they can get the user data. So the hacker sends it to the website server, then the website server will send that part to the API website.thm server, which will return the user data to the website instead of stock information, and then the website will return those user data to the hacker. This is an example of how an attacker can still reach the API user page with only having control over the path by utilizing directory traversal. So if you don't know what's directory traversal, you can go look at the file inclusion video link down below. So when the website here, as we can see, the expected request is URL equal /item ? ID equal the number. So instead of putting this, we'll use the directory traversal to get back to user. So it will be like URL equal /./ to go up one level, then user to get into the user. So the hacker still requests this to the website server, then the website server will send that request to the API website server, which will then return the user data to the website instead of stock information, and the website will return those user data to the hacker. Now, another example. So in this one, the attacker can control the server's subdomain to which the request is made. So take note of the end x equal being used to stop the remaining path from being appended to the end of the attacker's URL, and instead turns it into a parameter on the query string. So if the expected request is this one, so server equal, as you can see, it's stock ? server equal API and ID equal 123. So how the hacker will change it? Here, it turns out he will make it like this. So api.website.thm/API/user. So we get back to what we were looking for before, but just to put the rest of the request as a parameter, so as the value of the parameter x, he added or she added the end x equal. So all the thing that comes after is just the value for the parameter x. When the request gets sent to the website server will send that request to the API website server. And it goes from this thing here to still api.website.thm/API/user $x equal, and then the rest of the what would be inside the request. So website.website.thm/API/stock/item and ID equal 123. So when the server gets this request, it will return the user data to the website, and then the website will return those data to the hacker. So if we go back to the original request, the attacker can instead force the web server to request a server of the attacker's choice. By doing so, we can capture request headers that are sent to the attacker's specified domain. And these headers could contain authentication credentials or API keys sent by website.thm that would normally authenticate to API website.thm. So the expected request is still this one, so the first one that we saw in these examples. However, the hacker changed it to this. So as you can see, it goes to the hacker's domain. So when the hacker sends it to the website server, instead of sending the request to the API website, it will request data from the hacker domains instead of api.website.thm, and it could reveal the API key. Now, using what we've just learned, let's try using the address in the browser to force the web server to return data from server.website.thm/flag ID equal mine. As you can see, to make things easier, they've put the server requesting bar at the bottom just to show the URL that would be requested. If we like this, when we do API, what we found before, changing anything, that's what is requested. Now, what we want to get to is flag ID equal 9, that is from the host server.website. So let's change API to server. So we get to server.website. Let's just do this and see what the answer is. Not found. So now we have to make it like all the way to flag ID equal 9. So we'll add the rest of the URL, flag ID equal 9. So if we stop here, we won't have the answer that we are searching for. Why? Because if you can see here what it says, just after ID equal 9, there is everything else like .website, .thm, and so on and so forth. So what we want to do is add the x and x equal. So once we do that, we get the flag. Now that we've seen some SSRF examples, let's look at how or where we can find an SSRF. So potential SSRF vulnerabilities can be spotted in web application in many different ways. So sometimes we can find them when a full URL is used in a parameter in the address bar, for example here, like this, or hidden in a field form like this. This is a form, and we get inside of it an input with the type hidden, and the value is here. We can also find them as a partial URL used in a parameter in the address bar, like for example here, server equal API, or perhaps only the path of the URL like this. Some of these examples are easier to exploit than others, and this is where a lot of trial and error will be required to find a working payload. So when working with a blind SSRF, we'll need to use an external HTTP logging tool to monitor requests such as requestbin.com or our own HTTP server. Or again, another possibility would be using Burpsuite's collaborator client. So most security-savvy developers aware of the risk of an SSRF vulnerability may implement checks in their application to make sure the requested resource meets specific rules. There are usually two approaches to this, either a deny list or an allow list. Let's talk about the deny list first. So a deny list is where all requests are accepted apart from the resources specified in the list or that match a pattern. Why are deny lists used? It's to protect sensitive endpoints and also IP addresses or domains from being accessed by the public, while still allowing access to other locations. Specific endpoint to restrict access would be the local host, which may contain server performance data or further sensitive information. So, generally speaking, specific endpoint we want to restrict access to would be the local host, so domain names such as localhost or IP address like 127.0.0.1 would appear on a deny list. However, we would like to bypass this type of deny list. So how do we do that? By tricking it with DNS. So for example, using a subdomain that redirects to the IP address 127.0.0.1 using services such as nib.io. So let's just ping that subdomain and see that we'll end up with what? We'll end up with pinging our own IP address, our local host. So that's one way of doing it. We can also use IPv6 instead of IPv4. So maybe the protection for IPv4 haven't been implemented for IPv6. We also can try switching out the encoding. So using alternative localhost references such as O or 0.0.0.0.0 or 0000 or 127.1 or 127.0.0.0. We can use also octal encoding. So octal encoding means we are gonna use base 8 encoding. So for example, the 127.0.0.1 translates to 177.0.0.01 in octal. We have to put the 0 in front of 177 just to say that it's octal encoding instead of decimal like before. Let's try it out. So that would be ping 111.0.0.1. And again, we are still pinging our own localhost. We can also use hexadecimal instead of octal. So a hexadecimal is just using base 16 encoding, which means the numbers are from 09 to and AF. So A for 10, B for 11, and so on and so forth until F, which is 15, which makes the 127.0.0.1 translates to this. And you can try pinging this address and you'll see that it will still ping your localhost. We can also use D-words or double words. A double word is a 32-bit long integer. An IP address is a 32-bit number split into 4 octets, which means 1 octet is 8 bits, so 4 octets is 32-bit. So the 127.0.0.1 would translate to this number. We can also use URL encoding. So each character in a URL can be represented in its hex form using the % character before it. Like instead of localhost will translate to this, with each character, so for example L would be %6C, then O is %6F, and so on and so forth until the end. In a cloud environment, an address that is beneficial to block is the IP address 169.254.169.254. This contains metadata for the deployed cloud server, including possibly insensitive information. So an attacker could bypass this by registering a subdomain on their own domain with a DNS record that points to this IP address. The other way of securing against SSRF would be by using allow lists. So an allow list is where all requests are denied and part from the resources specified in the list or that match a pattern. So the deny list is we allow everything and just what is specified in the list or that is matching a pattern are denied, while the allow list is the complete opposite. We deny everything and only the resources that are specified in the list or that matches a pattern are allowed. So if an allow list is incorrectly implemented, for example, let's say that a URL used in a parameter must begin with this. An attacker could circumvent the rule by creating a subdomain like this. So it's still on its website, it's on its own domain, but it's started with website.thrm, or a directory like this. The application logic would now allow this input and let an attacker control the internal HTTP request. If all of the above bypasses don't work, we can still see if the open redirect works. So what is an open redirect? An open redirect is an endpoint on the server where the website visitor gets automatically redirected to another website address. So for example, we get this. So let's say that this endpoint was created to record the number of times visitors have clicked on this link for advertising, marketing purposes. But imagine there was a potential SSRF vulnerability with stringent rules which only allowed URLs beginning with website.thrm. So the attacker could utilize the above feature, this one, to redirect the internal HTTP request to a domain of the attacker's choice. Let's do the practice now. So in the previous videos we did some content discovery, and while doing content discovery exercise against this website, so Acme IT support website, we found these two: private and new account page, customer/new account page. Private gives us, if we go to private, so let's just do that. So if you go to private, it says you cannot access this page from your IP address. As for the second one, we need first to log in, and then we'll see that. So let's create an account first. Okay, so if you go to here, new account page, we see that there is a feature that allows us to choose an avatar for our account. Here there wasn't, but on the same, here there is. So let's look at the page source. And as you can, if we go down, the avatar images are here. So we get input type radio, name avatar, value equal this. So if we choose one avatar, let's use this one, and click on update, we get avatar updated and this. So let's again look at the page source. So the current avatar is now showing, and if we go to the page source, what we can find is current avatar background image. So the current avatar is displayed using the data URI scheme, and the image content is base64 encoded. So this is base64 encoded of the image. So now let's try making the request again, but let's try changing the value to private and see if the IP address block that we got when we were here, and let's see if the IP address block that we got can be passed through. So right click, inspect, And so instead of this value, let's just put private. And then update the avatar. So as you can see, it says the URL cannot start with /private. So because of that, let's try do some directory traversal, like something like directory traversal. So we have this assets avatars 6. So we remove all that and just let one letter, and then /.// and private, and let's update the avatar. Okay, this time avatar updated. However, there is nothing to look at here, so let's inspect this part. And what we can see is there is this in, so avatar image, background image, and so on and so forth. And then there's URL, data, image, PNG, base64, and some value. So let's copy this and put it here, and from base64, and here we go. We got the flag. I'm gonna talk about some common SSRF defenses that exist. So we talked about some of them before, but there are more defenses that exist. Like from a network layer point of view, we would segment remote resource access functionality in separate networks to reduce the impact. Also enforce the default deny firewall policies or network access control rules to block all but essential internet traffic. And from the application layer, as always, input validation, and again, input validation. Enforce URL schema, port, and destination with a positive allow list. Do not send raw responses to clients. Disable HTTP redirections, and be aware of the URL consistency to avoid attacks such as DNS rebinding and time of check, time of use race conditions. If you want to have more insight into how to defend against SSRF, you can read the OWASP SSRF prevention cheat sheet that I'll be linking down below. Thank you for watching today's video. I hope you enjoyed it. Don't forget to check out all the references and more reading material in the description box. Until next time, bye!